Hello everyone, today I'm excited to walk you through my process of building machine learning model to predict diabetes using the Pima Indians Diabetes Dataset. Before diving deep, let's talk about the tools and tech stack that I've leveraged. Firstly, I use Python for my primary programming language, then I use Jupyter Notebook and VS Code for interactive coding and scripting. I use Tableau for some intense data visualization. I use Streamlit for deploying the final model, and then several powerful Python libraries to process, analyze, and model our data. Okay, now we move to business problem and data understanding. Firstly, I want to show you the context of this problem. This dataset provided by Digital Scholar, which taken originally from the National Institute of Diabetes and Digestive and Kidney Disease. The objective is to predict based on the diagnosis measurement whether a patient has diabetes or not. Several constraints were placed on the selections of this instance from a larger database. In particular, patients here are females, at least 21 years old, of Pima Indian heritage. So the dataset consists of several medical predictor variables and one target variable outcome, and predictor variable include the number of pregnancies the patient has had, their BMI, insulin level, age, and more. Okay, about the problem. The problem in this project, Pima Indians have the highest rate of type 2 diabetes in the world, which is it's crucial to us for making models to predict early prediction, to give early prediction whether this person will have diabetes or not. The goals for this project: firstly, we want to create a machine learning model to predict patients who most likely have diabetes so they can maximize treatment for diabetic, thus their health condition is better in the future. Our target to create a machine learning with good performance to predict patient diabetic diagnosis. And then second, find out which factor that can influence diabetic diagnosis so that patient can determine more effective future handling based on their condition. And then lastly, we want to deploy this model to be a website-based system to make prediction. And then for make this project to get our goals, we will do this by this analytic approach. Firstly, we load the data to data conditioning, exploratory data analysis, preprocessing, modeling, search for optimal parameter of the model. It's include the hyperparameter tuning and other optimization process. And then we evaluate the model, we conclude and give recommendation, then we deploy this model. Okay, I will explain about the evaluation metrics that we use. Okay, for evaluation metric that best suit to this problem, which is machine learning supervised classification. There are some evaluation metric that can be used. Firstly, accuracy, and then confusion metrics like this, precision, recall or sensitivity, F1 score, ROC curve and AUC, specificity, and cost sensitive metrics. Okay, for diabetes prediction, recall or sensitivity is given high importance because it's critical to identify as many actual cases of diabetes as possible, or minimize false negative. However, this shouldn't come at the cost at very large number of false positive, which could lead to unnecessary stress for or medical intervention. Therefore, a balance, possibly using F1 score or considering both precision and recall, can be vital. Also, examining the ROC curve and maximizing the AOC can be a good strategy to ensure a good trade-off between sensitivity and specificity. So we will use ROC-AOC score for this problem. Okay, there are some evaluation metric that can be used for this problem. Okay, actually, for often recall or sensitivity is given high importance because it's critical to identify as many actual cases of diabetes as possible, minimize false negative. However, this shouldn't come at the cost of very large number of false positive, which could lead to unnecessary stress or medical intervention. Therefore, a balance, possibly using F1 score or considering both precision and recall, can be vital. Also, examining the ROC curve and maximizing the AOC can be a good strategy to ensure a good trade-off between sensitivity and specificity. So we will use ROC-AOC for a score for this problem. Then I want to explain about this false negative, false positive affect to this problem. True positive meaning that people who are predicted to be diabetic and are actually diabetic, and then true negative, people who are predicted to be diabetic but actually not. False positive, people who are predicted to diabetic but not actually diabetic. False negative, people who are predicted not to be diabetic but actually diabetic. So in this case, false negative, it's dangerous for the person because the diabetic person doesn't know that he has diabetes, so there is no treatment for them in dealing with diabetes problem. For false positive, loss of time and cost due to treatment even though the treatment is not needed. Furthermore, there is a potential effect on health condition when treating diabetes in people who are not diabetic. Okay, let's move to data understanding. The source of this data is a CSV file provided from Digital Scholar, but you can access these datasets through this link, which can downloaded by Kaggle. Okay, about the attribute, there are some attribute for the input variables. Its pregnancies is a number of pregnancies times glucose, plasma glucose concentration with 2 hours in an oral glucose tolerance test. Blood pressure, it's diastolic blood pressure. Skin thickness, recept skin fold thickness. Insulin, it's the insulin amount with method 2 hour serum insulin. BMI is a body in mass index. Then diabetes pedigree function and age. For outcome, outcome is a binary 1 or 2, whether this diabetes or not. Okay, next we will import dataset and libraries. First we need to install category encoder, and this if you using Google Collaboratory to download file CSV to your drive, you can install google.collab. Okay, there are several libraries that I use for this project. I use pandas and numpy for data manipulation, and then use matplotlib and cburn for visualization, and then XGBoost for advanced modeling and handling imbalanced dataset. I use IMBlearn, and then I use sklearn for some method to encode, transform, and use pipeline. Okay, this is the head of our data frame. Firstly, we need to condition the data frame. Actually, there are no missing value in these datasets, but I want to modify column name because it's more convenient for me to make this column name like this. Then next to explanatory data analysis, we will replace 1 in the y variable as yes, or explain that this data is diabetes, and 0 for no diabetes. And then we will handle missing value, anomaly, outlier, and duplicated data. Actually, there are no missing value indicated in this dataset. So we next to the data anomaly detection. As you can see in data anomalies detection, we see this data in glucose, blood pressure, skin thickness, insulin, and BMI have 0 value, which is not nonsense because glucose normally person don't have 0 value. Blood pressure also a person cannot get 0 in blood pressure. Also skin thickness, insulin, and BMI. So it probably happened maybe because of the data imputation process. They handle automatically missing value as 0 value, so there are no missing value but have 0 value in some of data point. Okay, for handle this, I will use machine learning based inputter. I use KNN imputer to assign 0 value to a value that based on the predictive model KNN. Okay, after data imputation, the distribution you can see like this. Okay, no have anomaly. Next, we will move to the outlier detection. In the data, we found some outlier in some attribute. For this case, I want to calculate first how many data outliers for each attribute. Okay, you can see this calculation based on the IQR. We found that the total of the outlier percentage is 9.1%, which is not really a big deal if we drop all this data point. So I will delete the data that is outlier. Okay, then we move to data duplicated detection. There are no data duplicated in these datasets. Okay, next to the feature engineering, we will make the new feature based on the existing feature. that we have wake status for engineering from the BMI. Okay, the BMI can be classification by underweight, health weight, overweight, obesity, type 1, type 2, and type 3. Okay, and then the insulin status. Insulin status, I classified as a normal insulin and abnormal insulin. And then for glucose status, I classify this from the glucose attribute, and then I classify by normal, pre-diabetes, and diabetes. Okay, but after binning this by the glucose status, there are no diabetes. There are no data in the diabetes classification, which is makes sense because we want to predict which data will be diabetes or not. Okay, about the blood pressure, I make blood pressure status by classification blood pressure in a normal or hypertension stage 1 or hypertension stage 2. Okay, now we move to data analysis. Okay, first we want to analysis univariate analysis. We will exploring for in each attribute. Okay, as you can see, this is the histogram for each attribute. There are variety for data distribution for all the attribute. It's like Poisson distribution. It's like a normal distribution but a bit skewed. Okay, next we want to find what the data distribution for each attribute. We will conducting normality test. For testing normality test in this dataset, I will use the Agostino-Pearson method, and then the Agostino-Pearson test interpretation is if we found p-value is larger than 0.05, we assume a normal distribution, but if smaller than 0.05, we cannot assume a normal distribution for this data. And then the result show that all the data feature we cannot assume a normal distribution. So for the further analysis, we will use non-parametric statistic. And then the percentage output of class as shown below. This no diabetes classified have amount of 67%, and then this dataset no indicated an imbalanced class. So we can see that 32% of patient indicated diabetes, and then this dataset doesn't indicate an imbalanced class between those who have diabetes and those who don't. We can see that 32% of patients indicated diabetes, and then This dataset doesn't indicate imbalance class between those who have diabetes on those who don't. Next to bivariate analysis. Okay, this is the pair plot between numerical feature. Some of attribute, we can see that they can well separated the class of diabetes and not diabetes, but there are some attributes also that cannot get the pattern to separate diabetes and not diabetes. And also there are a pair of attributes that this combination can well separate the class of diabetes or not diabetes. For example, glucose with BMI and age. So we will do further analysis based on glucose level, BMI, and age. From the pie chart, we can discern that 67.62% represent the category without diabetes, and then while the remaining 32.38% has been identified as having diabetes. Turning to the bar chart, for the age group 21 to 30, the class most susceptible to diabetes is categorized as level 3 obesity. Meanwhile, for age 31 to 40, the highest risk is attributed to level 1, 2, and 3 obesity classes. Within the 41 to 50 age group, the highest risk of diabetes is found among those ranging from overweight to level 3 obesity. Specifically in the level 3 obesity class, the risk is considerably high, with 9 individuals having diabetes with 4 without. This is highly risk for someone to have diabetes. Then for the age bracket of 51 to 60, over 50% belonging to the overweight to level 3 obesity class have pronounced risk for diabetes, with all these classes showcasing relatively high risk levels. Moving on the 61 and above age group, the most significant risk is observed in both level 1 and 2 obesity classes. In general, when we're focusing on BMI classes, the highest diabetes risk is found in level 1, 2, and 3 obesity. The paramount risk resides in level 3 obesity, where the risk ratio surpassed 50%, implying 43 individuals with diabetes in contrast to 38 without. In terms of blood pressure status classes, hypertension stage 2 harbors the highest risk, with 52 individuals having diabetes and 29 without. Furthermore, with the glucose status class, the class labeled as prediabetes has the most substantial potential for diabetes, with 106 individuals affected compared to 52 without. Delving into the insulin status class, those with an abnormal insulin status are at the pinnacle of risk, where 111 individuals have diabetes and 99 don't. Examining the data distribution for glucose, blood pressure, insulin, diabetes pedigree function, and BMI across various age range, none of these 5 variables distinctly segregate between the diabetes and non-diabetes categorized across age range. For instance, in the glucose class, as age advance, glucose level also rise. This trend is consistent across both categories as observed in blood pressure, insulin, and BMI as well. With insulin, the increase in age doesn't correspond to a sharp rise for those without diabetes. Meanwhile, for BMI, as age grows, BMI figures tend to diminish. Yet in the diabetes variable, the function prediction shows minimal difference between the diabetes and non-diabetes classes. Those with diabetes tend to have higher value as age progresses, but this trend is very mild. Conversely, those without diabetes experience a decline in the diabetes pedigree function as age increases. However, the trend line for this is minute, making it quite challenging and perhaps not effective to differentiate between these two classes. In conclusion, that is a comprehensive explanation of the relationship between these two variables as illustrated in the chart I crafted using W. Okay guys, let's move to data preprocessing. In the preprocessing schemas, I created 5 preprocessing schemas. First schemas, I am using data without feature engineering or DF, and then no preprocessing method applied to these schemas because they are already numeric feature. All is numeric feature, integer and float. So actually we can do directly modeling this data without any preprocessing schemas. And then the second schema, named transformer 1, I use data without feature engineering, same DF, but I conducting preprocessing, which is scalar. I use scalar in the robust scalar method on glucose, blood pressure, skin thickness, insulin, BMI, and age, because those are the variable who have different range. So to avoid different sensitivity on each variable, I use standardization, which is scaling in those variable. And that the third scheme is transformer 2, different with the previous two preprocessing schemas. In these schemas I use data after feature engineering, DFEDA1, which is the data frame that have additional feature from feature engineering, which is the glucose status, BMI status, insulin status, and blood pressure status. Then I use in preprocessing schemas one hot encoding on insulin status and glucose status, ordinal encoding in BMI group, blood pressure status, and then robust scalar in glucose, blood pressure, skin thickness, insulin, BMI, and age. And then fourth schemas is transformer tree. I use data after feature engineering DF EDA1, but I drop feature which is the original feature is a numeric feature: insulin, glucose, BMI, and blood pressure. Then I pre-processing, adding pre-processing scheme, one hot encoding for insulin status and glucose status, and ordinal encoding in BMI status and blood pressure status. Then still I use robust scalar in skin thickness and age. Then the last schemas is transformer 4. I'm using data without an feature engineering or DF, but I changed the pre-processing standardization method from robust scalar to quantile transformer on glucose, blood pressure, skin thickness, insulin, BMI, and age. This code is the pipeline for each pre-processing schemas, and I prepare each data frame for each pre-processing schemas. So here it is, schemas 1 using XS1 schema 1 train and XS1 test, YS1 train, YS1 test with no pre-processing schemas, etc. Then modeling. In modeling, I'm trying 7 method for benchmarking: logistic regression, decision tree, KNN, k-nearest neighbor classifier, and then random forest classifier, ADA boost classifier, gradient boosting classifier, and lastly XG boost classifier. Then I using a method for cross validation using scaffold with split size 5. This is the model benchmarking. I'm using cross validation k-fold with n split 5 for data training for each model benchmark. Then I use cross validation for data testing for each schemas. Okay, then I do comparison between each schemas and model. Okay, between 5 pre-processing schemas, schemas 1 have the best score for training and testing, so we will use schema 1 for further model optimization process. And between 7 models candidate, random forest have the highest score in the data training, and logistic regression have the highest score in data test. Based on the benchmark result, random forest has the highest mean cross validation score, approximately around 84%. However, logistic regression has the highest ROC score on the test, which is 74%. Therefore, logistic regression will be used for further process according to the test set score. Then this is the confusion matrix for logistic regression. Then this is for the gradient boosting, and this is for the XG boost. Okay, next we turn to the parameter tuning, hyperparameter tuning. Since we obtain ROC 74% from logistic regression model, we would like to increase the model's performance by using hyperparameter tuning. If the score improves, then the best parameters from this tuning will be used in the final model. Firstly, in model logistic regression, this is the best score. Best score, C score is 0.05. The solver is LBFGS, the class weight is balanced, the max iter is 100, multi-class is multinomial, random state is 2022, model penalty is L2. Then this is the score of logistic regression before and after tuning. This is comparison between before and after tuning. There are no improvement in erosi-ausi score between the model result before and after hyperparameter tuning. We choose use logistic regression before the tuning score in this section. So we can see that even we use hyperparameter tuning, that's not guarantee that we can have the highest the higher score in the test score than in the training score. And then the second model is gradient boosting. In gradient boosting, we get the best score is 85.5%, and the hyperparameter learning rate 0.1, max depth 2, minimum sample lift 0.1, minimum sample split 0.325, and estimator 64, random state 2022. And then these are the score for gradient boosting before and after tuning. For last model XGBoost, this is the hyperparameter tuning. Score is 85.2%, and then the hyperparameter is gamma 0, learning rate 0.1, max depth 5, and estimator 50, reg alpha 0, reg lambda 0.1. And then this is the score for XGBoost before and after tuning. Then we even though we know that this no have imbalance classification detected in the data frame, but we try to use undersampling and oversampling in terms to improve the scores of the model. Okay, this is the comparison between no treatment using random oversampling and using random undersampling. If we can see that there are no improvement with random oversampling, even with undersampling, so we still use still no need to use both oversampling or undersampling. And then we use feature selection. In those features that we require to this model, we find the coefficient which represent the importance of each variable that contribute to making the prediction in the model. Okay, for logistic regression, these are the attributes coefficient. Then we can see that the insulin and skin thickness have the lowest feature importance, so we try to drop these two variable, the attribute, then rerun the model without these two attributes. Okay, we can see that after feature selection process, the score is 74.38%, which no larger than using the tuning score before using feature selection is 74.3. So we don't have to drop these two variable, and then we do optimization process, which is logistic optimize threshold. In this optimization, we will use the threshold. We will use the condition after hyperparameter tuning, and then no need to drop any feature. Then we will find the best threshold for logistic optimization in range of 0.2 until 0.61, and then the result show that the best score is 74.8, which is not really improved significantly from last score we have. And then 74.8% result with the threshold of 0.47. So since there are no significant difference between changing the threshold, we don't need to change the threshold to 0.47 because I worry to the risk of changing this threshold, which not significantly affected to the score. Okay, this is the final score of this model. Accuracy 73.38%, precision 59%, recall 77%, F1 core 67, and ROC score 74%. Okay, the overall performance, the accuracy 73% means that 73 of prediction correct out of 100 prediction that we made from the model. That indicates a reasonably good classifier, especially if it is an initial or baseline model. Precision versus recall. Precision is 59%, and then out of all these cases where the model predicted diabetes, about 59% of them were true positive, while the rest are false positive. It's a moderate value, implying there might be a noticeable number of false alarms. Recall 77%. Out of all the actual diabetes cases, the model was able to identify nearly 78% of them. This is the fairly high recall, indicating that the model is well tuned to not miss out on actual positive cases. F1 score. An F1 score of 67.2% is a harmonic mean of precision and recall. It provides a single metric that balances the trade-off between precision and recall. This value is decent and indicates a somewhat balanced classifier in terms of false positive and false negative. ROC score of 74% is a metric that evaluates the classifier ability to distinguish between the positive and negative cases. A value of 74% indicates a good capability to differentiate between the two classes, especially given that a score of 50% would be no better than random guessing. We've seen the entire journey from understanding our business problem to deploying a machine learning model. It's been a comprehensive process leveraging several tools and techniques. Based on this project, we can conclude that the best model we can be created to predict someone will develop diabetes is a logistic regression with the hyperparameters C-score is 0.05, the solver LBFGS, the class weight is balanced, the max iter is 100, the multi-class is multinomial, the random state is 2022, the model penalty L2. The score result accuracy 73%, ROC score 74%, recall 78%, and precision 59%. The model is fairly good at identifying true diabetes cases as indicated by the high recall, but at the cost of producing a moderate number of false alarms as we've seen in the precision value. The ROC score above 70% is promising and suggests the model has a good understanding of the underlying pattern in the data. The features chosen to make these predictions are pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, and age. Then we have been deploy this model using this Trembling. Based on our finding, early intervention in high-risk patients can be crucial. Machine learning models like ours can aid healthcare professionals in making timely decisions. My recommendation for these projects are firstly, feature engineering. Besides our feature engineering in BMI, blood pressure, insulin, and glucose class, consider adding new feature or transforming other existing one to improve the model performance. And then model complexity. While logistic regression is a simple and interpretable model, it might not be able to capture all the pattern in the data. Consider trying more complex model in like random forest or gradient boosting, but remember to always use logistic regression as a baseline for comparison. And then resampling. Although we tried using undersampling and oversampling methods, which did not significantly affect the model result, we need to try use another method like synthetic minority oversampling techniques or SMOTE to handle imbalance even though the outcome proportion actually very balanced. Besides that, this dataset we well trained by data from Pima Indians race for women over 21 years old. So for making a better machine learning model that can be generalized to predict more a broad application, we need to consider using bigger data if it possible. Thank you for tuning in. I hope you find this comprehensive walkthrough enlightening. If you did, don't forget to like, share, and subscribe. Until next time, see you!